Hello everyone. Welcome back to my course Aerospace Engineering Rocket Science Basics. In this video, we will talk about brief history of rockets. Also, I will be thankful if you give me feedback about this course to make it better and more useful for you. Please write down your thoughts in the comment section or reach out to me via the email provided in my profile. Modern rockets represent an extraordinary achievement of human creativity and scientific understanding, but they did not appear suddenly or fully formed. Instead, today's rocket technology is the result of thousands of years of observation, experimentation, and gradual improvement in the understanding of motion and propulsion. The rockets used for space exploration, satellite launches, and scientific research are direct descendants of early ideas that explored how objects could be moved by expelling matter in the opposite direction. By studying these early developments, we can better appreciate how fundamental principles of rocket science were discovered long before they were formally explained by physics. Long before rockets were used for exploration or warfare, humans experimented with basic propulsion concepts, often without fully understanding the scientific laws behind them. These early experiments were driven by curiosity and ingenuity rather than formal theory. Over time, repeated trials and observations laid the groundwork for what would eventually become the science of rocketry. Each small advancement contributed to a growing body of knowledge about how motion could be produced without relying on wings, wheels, or direct contact with the ground. One of the earliest known devices to successfully demonstrate the essential principles of rocket flight was a wooden bird. According to the writings of Aulus Gellius, a Roman author, a Greek philosopher and mathematician named Archytas conducted a remarkable experiment around 400 BC. Archytas lived in the city of Tarentum, which is located in what is now southern Italy. His invention captured the attention and imagination of the local citizens because it appeared to defy the expectations of motion at the time. The device created by Archytas was a pigeon made of wood that could fly through the air. The bird was suspended on wires, and its motion was produced by steam escaping from its body. As the steam was expelled backward, it pushed the bird forward along the wire. Although simple in construction, this device demonstrated a core concept of rocket propulsion: motion produced by the expulsion of mass in the opposite direction. The wooden pigeon did not rely on flapping wings or external force, but instead moved due to the force generated by the escaping steam. This early experiment clearly illustrated what is now known as the action-reaction principle. In modern terms, this principle states that for every action, there is an equal and opposite reaction. When the steam rushed out of the wooden bird, an opposing force pushed the bird forward. While Archytas and his contemporaries did not express this idea as a formal scientific law, they observed its effects in practice. It was not until the 17th century that this principle was formally stated as a law of physics, yet its practical application had already been demonstrated more than 2,000 years earlier through this simple but ingenious experiment. Hero of Alexandria and the Eolipile. Approximately 300 years after the experiment of Archytas and his wooden pigeon, another Greek thinker made an important contribution to the early understanding of rocket propulsion. This individual was Hero of Alexandria, an engineer and inventor known for creating devices that demonstrated the practical use of scientific principles. Like the earlier experiment, Hero's invention relied on steam as a propulsive force, once again showing that controlled motion could be achieved through the expulsion of gas. Hero developed a device known as the eolipile, which is often considered one of the earliest examples of a rocket-like engine. Although it was not used for transportation or practical work, the eolipile clearly demonstrated how thrust could be generated by directing a flow of gas. The device consisted of a hollow sphere mounted on top of a water-filled kettle. This setup allowed heat energy to be converted into mechanical motion in a simple yet effective way. A fire was placed beneath the kettle, heating the water inside until it turned into steam. As the steam formed, it traveled upward through pipes that connected the kettle to the hollow sphere above. The sphere itself was free to rotate, allowing it to respond to the forces generated by the moving steam. This arrangement ensured that the energy produced by the steam could be transferred into motion rather than being released randomly into the surrounding air. On opposite sides of the sphere, Hero installed two L-shaped tubes. These tubes allowed the steam to escape in a controlled direction. As the steam exited through the bent tubes, it produced thrust in the opposite direction of the escaping gas. This thrust caused the sphere to spin around its axis. The rotation of the sphere was a direct result of the action-reaction principle, even though this principle had not yet been formally defined at the time. The eolipile did not serve a practical purpose beyond demonstration, but its importance lies in what it revealed about propulsion. It showed that continuous motion could be sustained as long as gas was expelled in a controlled manner. This concept is fundamental to modern rocket engines, which operate on the same basic idea, but with far more advanced materials, fuels, and engineering techniques. The emergence of the first true rockets. The exact moment when the first true rockets appeared in human history is not clearly known. Historical records from many different cultures contain scattered references to rocket-like devices, but these accounts are often incomplete or symbolic, making it difficult to determine precisely when rockets became distinct technological tools. Rather than emerging from a single invention or deliberate design, the earliest rockets may have been the result of chance discoveries and accidental observations. It is possible that the first true rockets were created unintentionally. In the 1st century AD, historical sources indicate that the Chinese had developed an early form of gunpowder. This mixture was made from saltpeter, sulfur, and finely ground charcoal dust. At the time, gunpowder was not used for propulsion or warfare as it would be in later centuries, but rather for entertainment and ceremonial purposes. During religious festivals, the Chinese used this gunpowder mixture to create explosions. They filled hollow bamboo tubes with the powdered ingredients and threw the tubes into fires. When exposed to heat, the mixture ignited, producing loud bangs and flashes of light that were meant to entertain or hold symbolic meaning during celebrations. These early explosive devices were not intended to move in a controlled way or travel through the air. However, not all of these bamboo tubes may have behaved as expected. In some cases, the tubes likely failed to explode completely. Instead of bursting open, the burning gunpowder inside produced hot gases and sparks that escaped through openings in the bamboo. As the gases rushed out, they may have pushed the tube in the opposite direction, causing it to shoot or skitter out of the fire. This motion would have been driven by the same action-reaction principle seen in earlier experiments with steam-powered devices. If such events occurred, they would have provided an early and dramatic demonstration of rocket propulsion using chemical energy rather than steam. Although accidental, these moving bamboo tubes may represent the earliest true rockets, as they carried both fuel and propellant within themselves and generated thrust through the rapid expulsion of gases. Over time, observations of these effects could have inspired more deliberate designs, eventually leading to the development of rockets intended specifically for propulsion rather than simple explosions. The birth of the true rocket in ancient China. After discovering that the gunpowder-filled bamboo tubes could sometimes move on their own, the Chinese began to experiment with these devices in a more deliberate way. Rather than using them only for ceremonial explosions, they explored how the tubes could be adapted to produce controlled motion. One of the earliest methods involved attaching the bamboo tubes to arrows and launching them using traditional bows. This combination allowed the devices to travel farther and more predictably than when thrown into fires. Through continued experimentation, the Chinese soon realized that the bow was not actually necessary. The gunpowder inside the tube could generate enough force on its own to propel the device forward. As the gunpowder burned, gases escaped from the open end of the tube, creating thrust that pushed the tube in the opposite direction. This realization marked a crucial turning point in the history of propulsion, as it demonstrated that a self-contained device could carry its own fuel and generate motion without external assistance. At this moment, the true rocket was born. Historical records indicate that the first documented use of true rockets occurred in the year 1232. During this period, China was engaged in warfare with the Mongols. One of the most notable engagements took place during the Battle of Kaikeng, where Chinese forces used rockets as part of their defensive strategy. These early rockets were known as arrows of flying fire, a name that reflected both their appearance and their fiery exhaust. The arrows of flying fire were a simple but effective form of solid propellant rocket. Each rocket consisted of a tube, sealed at one end and filled with gunpowder. The opposite end of the tube was left open to allow the exhaust gases to escape. The tube was then attached to a long stick, which served an important stabilizing role during flight. When the gunpowder was ignited, it burned rapidly, producing flames, smoke, and hot gases. As these gases rushed out of the open end, they generated thrust that propelled the rocket forward through the air. The attached stick functioned as a basic guidance system. While it did not allow for precise control, it helped keep the rocket pointed in a general direction and prevented it from tumbling unpredictably during flight. This simple stabilization method made the rockets more reliable and increased their effective range. Although it is unclear how much physical damage these arrows of flying fire caused, their psychological impact on the Mongol forces was likely significant. The sight and sound of flaming projectiles streaking through the air would have been both unfamiliar and terrifying. Even if their destructive power was limited, these early rockets demonstrated the potential of rocket technology in warfare and marked an important milestone in the evolution of rocket science. The spread of rocket technology to Europe. After the Battle of Kaikeng, rocket technology did not remain confined to China. The Mongols, having encountered rockets on the battlefield, began producing rockets of their own. Through their extensive conquests and wide-ranging contact with other cultures, they may have played a key role in spreading knowledge of rockets westward. As a result, rocket concepts gradually made their way into Europe, where they sparked curiosity and experimentation among scholars, inventors, and military engineers. From the 13th through the 15th centuries, historical records contain numerous references to rocket experiments across Europe. During this period, rockets were still relatively crude and unreliable, but steady progress was made through trial and observation. Experimenters focused on improving propulsion, stability, and range, often working with different formulations of gunpowder and various launch methods. These efforts marked an important transition from accidental discovery to intentional technological development. In England, a monk named Roger Bacon played a significant role in advancing rocket technology. He conducted research on improved forms of gunpowder, refining the proportions of its ingredients to produce more powerful reactions. These improvements greatly increased the range of rockets, making them more effective for both experimental and military purposes. Bacon's work demonstrated how careful study of chemical composition could directly influence the performance of rocket propulsion. In France, Jean Froissart contributed to rocket development by addressing the problem of accuracy. He discovered that launching rockets through tubes could result in straighter and more predictable flight paths. By constraining the rocket's initial motion, the launch tube helped guide it in the desired direction before it entered free flight. This concept represented a major step forward in rocket guidance and stability. Froissart's idea later served as the foundation for modern shoulder-launched rocket systems, such as the bazooka. Meanwhile, in Italy, Johannes de Fontana explored more unconventional applications of rocket propulsion. He designed a surface-running, rocket-powered torpedo intended to set enemy ships on fire. This device was meant to travel across the surface of the water, driven by rocket thrust, until it reached its target. Although such designs were largely experimental, they illustrated the growing awareness that rockets could be used in a variety of roles beyond simple aerial projectiles. These European experiments collectively helped expand the scope and understanding of rocket technology during the Middle Ages. Rockets in the 16th century, fireworks, step rockets, and legends of flight. By the 16th century, the use of rockets as weapons of war had largely declined. Advances in artillery and firearms made rockets less practical on the battlefield, and they became more associated with entertainment and ceremonial displays. Fireworks, in particular, provided a popular outlet for the continued experimentation with rocket technology. Artisans and inventors explored creative ways to make fireworks more impressive, higher reaching, and visually spectacular. One notable figure during this period was Johann Schmidlapp, a German fireworks maker who made a significant contribution to rocket design. Schmidlapp invented what he called the step rocket, an early form of a multi-staged rocket. This ingenious concept involved stacking a smaller rocket atop a larger one. The larger first stage rocket carried the smaller second stage rocket to a higher altitude. Once the first stage burned out, the second stage rocket ignited and continued its flight even higher before releasing a brilliant shower of glowing cinders into the sky. Although originally intended for fireworks, the principle behind Schmidlapp's step rocket, using multiple stages to reach greater heights, is fundamental to modern rockets that travel into space. Today, virtually all spacefaring rockets, from satellites to interplanetary spacecraft, rely on this same multi-stage concept. While nearly all rocket use up to this time centered on warfare or entertainment, there are intriguing stories and legends that suggest even bolder ambitions. One such tale comes from China, where a lesser-known official named Wan Hu reportedly attempted to use rockets as a means of transportation. According to the legend, Wan Hu assembled a flying chair powered entirely by rockets. The chair was attached to two large kites, and fixed to the kites were 47 fire arrow rockets. On the day of the flight, Wan Hu is said to have seated himself on the chair and commanded his assistants to light the rockets. 47 attendants, each carrying a torch, rushed forward to ignite the fuses. Almost immediately, a tremendous roar erupted, accompanied by thick clouds of smoke. When the smoke finally cleared, Wan Hu and his flying chair were nowhere to be seen. The legend does not provide a clear outcome, and it is widely believed that if the event truly occurred, the rockets exploded rather than lifted Wan Hu into the sky. Fire arrow rockets were highly unpredictable. They could propel objects forward, but they were equally likely to explode in a dangerous and uncontrolled manner. Although the story of Wan Hu is likely more myth than reality, it reflects a long-standing fascination with human flight and the potential of rockets to achieve it. Even in the 16th century, the imagination and ingenuity of inventors were already envisioning uses of rocket technology far beyond fireworks and battlefield applications, foreshadowing humanity's eventual journey into space. Rocketry becomes a science. During the latter part of the 17th century, the foundation for modern rocketry began to shift from experimentation and legend to formal scientific understanding. This transformation was largely due to the work of the English scientist Sir Isaac Newton, who lived from 1642 to 1727. Newton developed a systematic description of motion through his three groundbreaking laws of physics. These laws not only explained how objects move on Earth, but also provided the theoretical framework for understanding how rockets operate, including their ability to function in the vacuum of outer space where there is no air to push against. Newton's laws clarified the principles behind propulsion. The first law, often called the law of inertia, explains that an object will remain at rest or continue moving in a straight line unless acted upon by an external force. The second law relates force, mass, and acceleration, showing how the thrust produced by a rocket's engine determines its acceleration. The third law, famously summarized as "for every action, there is an equal and opposite reaction," directly describes how rockets move. As gases are expelled in one direction, the rocket is propelled in the opposite direction. With these laws, the movement of rockets could be predicted, calculated, and eventually optimized, turning rocketry from a craft based on trial and error into a field guided by science. By around 1720, these ideas began influencing practical experiments. A Dutch professor named Willem Gravesand built model vehicles propelled by jets of steam, demonstrating the principles of action and reaction in controlled settings. Meanwhile, rocket experimentation in Germany and Russia was expanding to larger, more powerful devices. Rockets with masses exceeding 45 kilograms were constructed, and some were so forceful that the exhaust flames escaping from their engines dug deep holes in the ground even before the rockets lifted off. These early large-scale experiments showcased both the potential and the dangers of rocket propulsion, highlighting the need for careful calculation and design. With the application of Newtonian physics, rocketry began to evolve from folklore, fireworks, and accidental discovery into a true science. Engineers and experimenters could now understand why rockets worked, predict their motion, and gradually improve their designs with precision. This shift marked the beginning of the era in which rockets would eventually move from the ground to the skies and, centuries later, into outer space. The revival of rockets as weapons of war. At the end of the 18th century and into the early 19th century, rockets experienced a brief resurgence as military weapons. This revival was largely inspired by the effectiveness of Indian rocket barrages against British forces in 1792 and again in 1799. The spectacular displays of fire and destruction caught the attention of British artillery expert Colonel William Congreve, who saw the potential to adapt and improve rockets for European warfare. Motivated by these early successes, Congreve set out to design rockets that could be deployed systematically by the British military. The rockets developed by Congreve, aptly named Congreve rockets, proved highly effective in battle. They gained particular fame during the War of 1812, when British ships bombarded Fort McHenry using large volleys of these rockets. The impressive sight of flaming projectiles arcing through the night sky inspired Francis Scott Key to write the words "the rocket's red glare" in his poem, which later became part of the lyrics of the Star-Spangled Banner. Although Congreve rockets were visually dramatic and psychologically intimidating, their accuracy remained limited. Much like the rockets of earlier centuries, their destructive power came primarily from sheer numbers rather than precise targeting. During a typical siege, thousands of rockets could be launched at the enemy, creating chaos and fear even if relatively few found their intended targets. Efforts to improve rocket accuracy became a major focus for European researchers. One notable breakthrough came from the Englishman William Hale, who developed the technique of spin stabilization. In this method, small vanes were placed at the base of the rocket, angled in such a way that the escaping exhaust gases caused the rocket to spin along its axis. This spin, similar to the rotation of a bullet fired from a rifled barrel, helped stabilize the rocket's flight and improve its trajectory. Variations of spin stabilization are still applied in modern rocketry, particularly in smaller rockets and projectiles, demonstrating the lasting impact of Hale's innovation. Despite these advancements, rockets eventually faced limitations against evolving military technology. On the European continent, rockets continued to see use in various battles, but during a conflict with Prussia, Austrian rocket brigades encountered artillery that rendered them obsolete. Breech-loading cannons with rifled barrels and explosive warheads were far more accurate and deadly than even the most powerful rockets. As a result, rockets were once again pushed out of military prominence and returned to peacetime applications, including fireworks, signaling, and experimental studies. This cycle of military use, followed by decline, illustrates the ongoing tension between technological innovation and practical effectiveness in the history of rocketry. Modern rocketry begins. The true beginning of modern rocketry can be traced to the work of Konstantin Tsiolkovsky, a Russian schoolteacher and visionary who lived from 1857 to 1935. Unlike the inventors and experimenters of earlier centuries, Tsiolkovsky approached rocketry not as a curiosity, a weapon, or a tool for fireworks, but as a scientific means of exploring space. He imagined a future in which humans could leave the Earth and travel among the stars, and he dedicated himself to understanding how rockets could make such journeys possible. In 1898, Tsiolkovsky first proposed the concept of space exploration using rockets, an idea that was revolutionary for its time. Many scientists still viewed space as unreachable, and rockets were largely seen as toys or military devices. Tsiolkovsky, however, applied the principles of physics, building on the work of Newton and others, to show that rockets could, in theory, function in the vacuum of space, where there is no air to push against. In 1903, Tsiolkovsky published a groundbreaking report in which he outlined the use of liquid propellants for rockets. Unlike solid gunpowder rockets, liquid propellants could be controlled, throttled, and ignited in stages, offering far greater flexibility and range. Tsiolkovsky recognized that the performance of a rocket depended fundamentally on the speed at which its gases were expelled, later known as exhaust velocity. He demonstrated that, in principle, the speed and range of a rocket were limited only by this velocity and by the mass of the propellant carried aboard. Tsiolkovsky's ideas went beyond engineering. They represented a profound vision of humanity's future in space. His theoretical work laid the foundation for all modern astronautics, influencing later pioneers who would turn spaceflight into reality. Because of his careful research, scientific insight, and bold imagination, Konstantin Tsiolkovsky is widely recognized today as the father of modern rocketry and astronautics. Robert H. Goddard and practical rocketry. Early in the 20th century, the theoretical ideas of Konstantin Tsiolkovsky began to find practical expression in the work of Robert H. Goddard, an American scientist and engineer who lived from 1882 to 1945. Unlike Tsiolkovsky, whose work was largely theoretical, Goddard focused on turning the principles of rocketry into functioning machines. He was motivated by a desire to reach higher altitudes than could be achieved by lighter-than-air balloons, which at the time were the primary means of exploring the upper atmosphere. In 1919, Goddard published a pamphlet titled A Method of Reaching Extreme Altitudes, which represented a pioneering application of mathematics to rocket flight. In this report, he outlined calculations and design principles for what is now known as the meteorological sounding rocket, a rocket specifically designed to carry instruments into the upper atmosphere to gather scientific data. This work demonstrated that careful study of physics and engineering could transform rockets from experimental curiosities into reliable tools for scientific exploration. Goddard's early experiments began with solid propellant rockets, the type of rocket used for centuries in warfare and fireworks. By 1915, he was experimenting with various solid fuels, carefully observing their burning characteristics and measuring the velocity of the gases they produced as they burned. These measurements were crucial because the speed at which exhaust gases are expelled directly determines the thrust a rocket can generate. Through systematic testing, Goddard developed a precise understanding of how different fuels and designs affected rocket performance, laying the groundwork for the more advanced liquid-fueled rockets that he would later develop. In essence, Goddard's work marked a shift from experimentation based on trial and error to an engineering-based approach in which calculations, measurements, and careful experimentation guided the design of rockets. His research not only demonstrated the feasibility of achieving extreme altitudes, but also established methods and principles that would influence rocket development for decades to come. While experimenting with solid propellant rockets, Robert H. Goddard became convinced that a rocket could achieve far greater performance if it were fueled by liquids instead of solids. Liquid propellant rockets offered the potential for higher thrust, longer flight times, and more precise control, but at the time, no one had ever successfully built one. Unlike solid rockets, liquid rockets required complex systems, including separate tanks for fuel and oxidizer, turbines to pump the liquids, and carefully designed combustion chambers where the propellants could mix and ignite safely. These challenges made liquid propulsion a far more difficult engineering problem than working with solid fuels. Despite these obstacles, Goddard achieved a historic breakthrough on March 16, 1926. On that day, he launched the world's first successful liquid propellant rocket, fueled by liquid oxygen and gasoline. The flight itself was modest. The rocket flew for only 2.5 seconds, reached a height of 12.5 meters, and landed 56 meters away in a cabbage patch. By modern standards, this performance might seem insignificant, but in the context of history, it was monumental. Just as the Wright brothers' first powered airplane flight in 1903 opened the door to aviation, Goddard's small gasoline rocket marked the beginning of a new era in rocketry, proving that controlled, powered flight using liquid fuel was possible. Goddard did not stop there. Over the following years, he continued to experiment with liquid propellant rockets, gradually building larger machines capable of higher and longer flights. He introduced innovations that would become standard in modern rocketry, including gyroscope-based flight control systems to stabilize rockets in flight, payload compartments for carrying scientific instruments, and parachute recovery systems to safely return both rockets and their instruments to the ground. These developments allowed rockets to be used not only as experimental vehicles, but also as tools for scientific research, laying the foundation for future exploration of the atmosphere and space. For these groundbreaking achievements, Robert H. Goddard is widely recognized as the father of modern rocketry. His pioneering work demonstrated that liquid-fueled rockets were practical and controllable, and his methods, designs, and principles continue to influence rocket science to this day. Hermann Oberth and the foundations of modern spaceflight. A third major pioneer in the history of rocketry and space exploration was Hermann Oberth, born on June 25, 1894, in Hermannstadt, Transylvania, and who lived until December 28, 1989, in Nuremberg, Germany. Oberth was a visionary thinker whose work bridged the gap between theoretical rocketry and practical space travel. In 1923, he published a groundbreaking book on rocket travel into outer space, presenting calculations, designs, and ideas that demonstrated that human flight beyond the Earth's atmosphere was possible. His writings inspired a generation of engineers, scientists, and enthusiasts to seriously explore rocketry as a means of reaching space. Oberth's influence led to the formation of numerous small rocket societies around the world, including the German Verein für Raumschifffahrt, or Society for Space Travel. These societies became incubators for experimentation, technical collaboration, and innovation. In Germany, this movement eventually contributed to the development of the V-2 rocket, one of the most advanced rockets of its time, which would later be used against London during World War II. By 1937, German engineers and scientists, including Oberth, gathered at Peenemünde, a research facility on the shores of the Baltic Sea, to develop the V-2 rocket under the leadership of Wernher von Braun. The V-2, also known in Germany as the A-4, was small compared to modern rockets, yet it achieved extraordinary thrust by burning a mixture of liquid oxygen and alcohol at a staggering rate of approximately 1 ton every 7 seconds. Once launched, the V-2 was capable of devastating entire city blocks, demonstrating the immense destructive potential of liquid-fueled rockets. Despite its power, the V-2 arrived too late in the war to influence the outcome in Europe. Nevertheless, German rocket scientists had already conceived plans for more advanced missiles, including intercontinental designs capable of spanning the Atlantic Ocean and delivering payloads to the United States. These advanced concepts included winged upper stages, though the payload capacities would have been relatively small. When Germany fell, many V-2 rockets, components, and scientific knowledge were captured by the Allied forces. Numerous German scientists, including Wernher von Braun, relocated to the United States, while others went to the Soviet Union. In both cases, the scientists were impressed by the pioneering work of Robert H. Goddard, whose experiments with liquid-fueled rockets had predated and anticipated much of their own work. Recognizing the potential of rocketry as both a military and scientific tool, the United States and the Soviet Union initiated experimental programs to advance rocket technology. In the United States, these efforts began with high-altitude atmospheric sounding rockets, directly inspired by Goddard's early experiments. Over time, the programs expanded to include medium and long-range intercontinental ballistic missiles, which became the technical foundation for the U.S. space program. Rockets, such as the Redstone, Atlas, and Titan, eventually evolved to carry astronauts and satellites into space, realizing the vision first imagined by Tsiolkovsky, Goddard, and Obert decades earlier. The legacy of Hermann Oberth lies not only in his own work, but also in the networks of scientists, engineers, and societies he inspired. His writings provided a theoretical roadmap for space travel and laid the intellectual groundwork for the rockets that would eventually take humanity beyond Earth. The dawn of the space age. On October 4, 1957, the world witnessed a historic moment that would change the course of human history. The Soviet Union successfully launched Sputnik 1, the first artificial satellite to orbit the Earth. This event stunned the global community, marking the beginning of the space age and igniting a competitive race for space exploration between the two emerging superpowers, the Soviet Union and the United States. Sputnik 1 was a small, simple satellite, yet its launch demonstrated the technological capability to place objects into orbit, a feat that had been long theorized but never before achieved. Less than a month after Sputnik 1, the Soviets launched another satellite, this time carrying a living passenger, a dog named Laika. Laika's mission provided the first opportunity to study the effects of space travel on a living organism. The dog survived in orbit for 7 days before being put to sleep to prevent suffering once her oxygen supply was exhausted. Laika's flight, though tragic, offered invaluable insights into life support systems, the effects of weightlessness, and the challenges of sustaining living beings in space. The United States quickly responded to the Soviet achievements. On January 31, 1958, the U.S. Army successfully launched its first satellite, Explorer 1, into orbit. This marked America's entry into the space race and represented a crucial step toward understanding Earth's upper atmosphere and near-space environment. Explorer 1 carried scientific instruments that led to the discovery of the Van Allen radiation belts, highlighting the mission's importance for both science and national prestige. Later that year, in October 1958, the United States formalized its commitment to space exploration by creating the National Aeronautics and Space Administration, NASA. Unlike military programs, NASA was established as a civilian agency with the goal of peaceful exploration of space for the benefit of all humanity. Its creation centralized American efforts in rocket development, satellite launches, and space science, setting the stage for ambitious missions, including crewed spaceflight, lunar exploration, and interplanetary research. The launch of Sputnik 1, Laika's historic journey, and the creation of NASA collectively marked the beginning of a new era in which humanity would move beyond the Earth, transforming rocketry from a tool of science and warfare into a vehicle for exploration and discovery across the solar system. Rockets opened the universe. As the space age progressed, rockets became the vehicles that carried both humans and machines beyond Earth's atmosphere. Astronauts began orbiting the planet, experiencing weightlessness and observing Earth from a new perspective. Eventually, humans set foot on the moon, fulfilling a centuries-old dream of traveling to another celestial body. At the same time, robotic spacecraft were sent, explored the planets, providing humanity with detailed images, measurements, and knowledge about worlds that were once completely inaccessible. The expansion of space exploration also brought practical and commercial benefits. Satellites became essential tools for science, enabling meteorologists to forecast the weather more accurately, allowing geologists and oceanographers to study Earth's surface, and providing the infrastructure for instant global communications. Each of these applications relied on increasingly capable rockets to deliver larger and more sophisticated payloads into precise orbits. As demand for these capabilities grew, engineers designed a wide array of powerful and versatile rockets, ranging from medium lift launch vehicles to massive boosters capable of sending humans and instruments to distant planets. From their earliest beginnings as simple gunpowder devices to the giant, complex machines of today, rockets have undergone an extraordinary evolution. They have transformed from experimental curiosities and weapons into tools that enable humans to explore space directly. By harnessing the principles of physics, chemistry, and engineering, rockets have opened the universe to observation, research, and discovery, turning what was once imagination and legend into a reality that continues to expand our understanding of the cosmos. Okay guys, now let's have a little quiz. The quiz consists of 5 questions. I'll give you 10 seconds for each one, and then I'll show you the correct answer. Let's start with the first question. Question 1. Who is widely recognized as the father of modern astronautics for proposing the use of liquid propellants in rockets? The correct answer is Konstantin Tsiolkovsky. Question 2. What was the main achievement of Robert H. Goddard on March 16, 1926? The correct answer is he conducted the first successful liquid propellant rocket flight. Question 3. The wooden pigeon of Archytas and hero of Alexandria's Aeoli pile demonstrated which scientific principle? The correct answer is the action-reaction principle. Question 4. Which event marked the beginning of the modern space age? The correct answer is launch of Sputnik 1 by the Soviet Union. Question 5. What was Johann Schmidlap's invention of the step rocket primarily used for? The correct answer is multi-stage fireworks to reach higher altitudes. Unlock the world of aerospace engineering with my other expertly designed courses. In Aerospace Engineering, Basics of Aviation Engines, you'll explore the different types of aerospace engines and how they perform, giving you a strong foundation in the propulsion systems that power modern aircraft. Then, take your knowledge to new heights with Aerospace Engineering, Aerodynamics and Structures, where you'll dive into the design and performance of aerospace structures and their aerodynamic behavior. Finally, expand your expertise with Aerospace Engineering, Avionics and Aerospace Systems, where you'll learn about the critical electronic systems that control and monitor modern aircraft, bridging the gap between engines, structures, and flight systems. Whether you're a student, aspiring engineer, or aviation enthusiast, these courses will equip you with essential knowledge to understand and contribute to the future of aviation. Join hundreds of learners and start building your aerospace journey today. Thank you guys for watching this video. If you have any questions about this lesson, feel free to ask me in the comment section. I will answer as soon as possible. We can continue to the next lesson and learn about standard atmospheric model. See you in the next video. Bye.